Hi guys, so this is your video about combined variation. So there are multiple types of variation functions. This one is focusing on combined variation. So the trick with combined variation is that it is a combination of variations. Specifically, combined variation is a combination of direct variation, which is y equals kx, and inverse variation, which looks like y equals k over x. So we end up with something like y equals kx over z. So there's both multiplication and division. All right. So with that, let's talk about an example. The nice thing about these problems is it will tell you which is which. So it says the volume V of a gas varies inversely with the pressure P and directly as the temperature T. So let's talk about what are our three variables. We have the volume, we have the pressure, and we have the temperature. Those are going to be our y, x, and z. Not necessarily in that order. Because now we would say, okay, the volume varies inversely. So the volume varies inversely as the pressure. So that's going to be my y and x for my inverse portion of my formula. So this is going to be V equals K over P. So P is the inverse, so it's going to be in the denominator. And directly as the temperature. So direct variation is the multiplication one. So that's where the temperature is going to live. So the temperature is going to be the multiplication in the numerator, like so. So it tells you exactly where each part goes. Now let's put it in a context of a specific gas. A certain gas has a volume of 10 cubic liters at a temperature of 300 degrees Kelvin and a pressure of 1.5 atmospheres. So that would be our V, T, and P respectively. Now if we know V, T, and P, the only thing we don't know is K. And K is, of course, our variation constant, as it is with all variation functions. So we need to solve for K, because as soon as we try to apply it to a new scenario, we need that constant. So let's plug in what we know. Our volume is 10 equals, we don't know our constant, times our temperature, which is 300, divided by our pressure, which is 1.5. Now we need to solve for K. So the first thing we're going to do is get rid of the division by 1.5. At least that's one way you could do it. That's what I'm going to do, just because I don't like dealing with those fractions when it's possible to get rid of them. So I'm going to multiply by 1.5 on both sides, which is going to give me 15 equals 300K. Now to get K by itself, I need to divide off the 300. Cancels here, so I get 0.05 equals K. So now we have our decay constant. Now we can deal with our second part of our problem. It says if the gas, meaning the same gas we're talking about, so the constant is the same, if the gas, so that's why we needed our decay constant, because that decay constant relates to this specific gas. is compressed to a volume of 7.5 liters. So there's our new volume. And is heated to a temperature of 350 degrees Kelvin. So that's our new temperature. What is the new pressure? So I want to solve for P. So I'm going to plug in what I know. I know K, I know K, V, and T. So I'm going to plug in my volume. There we go. Is 7.5. I know my decay constant is 0.05. I know my new temperature is 350. What I don't know is my pressure. So to solve for pressure, just like we did before, I'm going to get rid of the fraction. I'm going to multiply by P on both sides so that I can cancel out this fraction. So I'm going to have 7.5 P on the left equals, and then if I just do that multiplication in the numerator real quick, I'm going to get 17.5. Now I can solve for P. I can divide off the 7.5, and I get P equals 2.3 repeating. There it is. I hope that helped.